So hi, good afternoon everyone. So today I'm presenting on this topic called the n-body problem. It's a very classical problem that physicists solved in the past few centuries. Nowadays we move on to much more advanced stuff, but this thing is nevertheless very interesting for us to explore. So what is the n-body? So one of the most dominant n-body problems that we see in our daily life is basically the solar system. So the solar system has the sun, the planets, the moons, and satellites. So basically what we study is, we want to study how these things interact with each other. And how do they interact? For large bodies like this, they'll interact through gravitation force. So basically for a typical three-body system where you imagine there's only three items, so each item will experience an acceleration, and this acceleration is caused by the attraction of gravity between one mass to another. So if you have three bodies, then you will imagine that the first body will experience two forces, right? Imagine now you have a solar system, you have millions of bodies, millions of satellites, millions of little rocks and asteroids. Then you will have an exploding number of equations here. Super difficult to solve. But let me give you some examples. So we saw this three-body system here. And basically what I want to do today is I just want to demonstrate the complexity of a many-body system. Yeah. How a simple problem like attraction can possess so much variance to it. And another thing is maybe just to have fun and maybe learn a few things. So if you look at the picture here, you realize that everything has the same starting point, but because of the different initial conditions, the orbit can look totally different. So let me show you an example. Now let's look at the Sun, Earth, and Moon system. So I can show you the simulation of how they run in real life. So the dot in the middle is the Sun, the little light ball, blue ball is the Earth, and this thing oscillating up and down is our Moon. So this is the 3D view. And then if you look at 2D, you realize that, okay, the Sun is here, the Earth is following the orbit, which is according to what we believe is happening. You can't see the Moon here because the Moon is too close to the Earth. But from a zoom up shot, you can actually see that this little thing Moon is circulating the Earth. One round with the same periodicity. So quite interesting, huh? So, but then I would like to pose you a question. What will happen if I triple the mass of the Sun? You can go to menti.com and use the code to fill out your what do you think will happen? So remember that gravitational force is a force of attraction. The heavier you are, the stronger the attraction force is. What will happen if the mass of Sun becomes 3 times the current mass? Everybody is very scientific. So let's see what will happen. There's a reason why many-body problems are considered one of the hardest problems to solve, because there's no analytical solution. Everything is unpredictable. So let's see what will happen. So if you look at the 3D view, you see that our little moon oscillates for a bit and it gets catapulted out from our entire so-called original system. Quite interesting, isn't it? So now our moon becomes a new mini planet of the Sun. This is because when the Sun try to pull the moon with a stronger force, the moon gets too close to the Earth, and the gravitational force acts as a trebuchet that launches the moon out of the entire moon and Earth system. So a little bit different from what you have expected, right? So now let's try again. Let's do a comparison of these two. Periodic, very nice, beautiful world that we live in. But if something happens to the Sun, disaster. Let's try again, another question. What will happen if the moon becomes as heavy as Earth? And then we can try this question on the vacuum. actually stop believing in logic. Okay, let's see what will happen there. So let's look at the 2D view and the zoom in shot. So for the 2D view, the Earth still seems to surround the Sun at a very nice regular pace. The orbit doesn't seem to change much, not really affected by the mass of the Moon. And you can see that the Moon is still oscillating around Earth, just a little bit quicker, probably because the force of attraction is higher. But now let's look at the 3D plot. Notice something different. Now Earth and the Moon forms a bi-body system that oscillates each other. So now you have a very nice helix ring around the Sun. Yes, something magical. So to end off, I would just like to show you the entire simulation of all the major bodies of the solar system. So we have all the planets here, and including the little Pluto that we decided to discard. And then you can actually see very clearly why Pluto is discarded, because look at every planet's orbit and look at Pluto's orbit. It's the anomaly.
So was Pluto once a moon?
No, Pluto is considered a different type of planet, not entirely belonging to the solar system. Yeah. So again, the purpose was just to show you that it is impossible to analytically predict the n-body system, and all we can do is use the numerical method to simulate. And that's all for my presentation. Thank you. And if you're interested, you can Google n-body problem. There's more mathematics there.
Thank you.